Shor's algorithm requires the new operator we never met before in this course, the quantum Fourier transform, the QFT. The definition of this operator you see here on the slide. And for those of you who are familiar with signal processing, I bet this expression looks familiar. And from now on, we are going to use this notation. So big N is now 2 in the power small n, where n small is number of qubits. And as always, we start with a check. We check if I didn't trick you by introducing some operator which is not unitary. So we have to check the unitarity of QFT. And we start with the norm. We are going to check if QFT preserves norm. So we have this squared norm here of some vector x, and we're going to see what it equals to. So we have this squared norm of x here, and 2 in the power n here, and a big dot product of two sums over all y's, each sum over all these y's from 0 to 2 in the power n minus 1. On the first place, e minus 2p I xy divided by n y. And on the second place, this sum is plus 2p I x, y, and y. And of course, these counters are different, so we may denote this y1 and y2 here. Okay, now we are going to split this sum this way. In the first place, we are going to place the sum over different y's. y1 does not equal to y2. And we have some exponents and dot product of y1, y2, which is 0 because y1 and y2 are different basis vectors. So this part is 0 plus the sum over equal y's, e minus 2p I x, y 1 divided by n, and since y2 equals to y1, we can write exponent 2p I x, y 1 again divided by n multiplied by y1, y1. Okay, this obviously equals to 1, and this, since it is the same basis vector, also equals to 1. Okay, and the number of terms in this sum is exactly 2 in the power n, which is n big. So we have 2 in the power n of ones, and the total sum multiplied by this is exactly x squared. So check past, and QFT preserves the norm. Let's see what it does with the angles. Okay, let's see if QFT preserves angles. Now we know it preserves the norm, so instead of the norm here we can write just 1, since we work only with unit vectors in our spaces. And we have two different basis vectors here, orthogonal vectors x1 and x2, and we apply QFT to them, and we see what happens to the dot product. Okay, we have 1 divided by 2 in the power n, and again dot product of the sums or y1 and y2, and we already know that for different y1 and y2 the dot product is 0, so we recognize that by writing this over the same y, one sum over the same y, e in the power minus 2p I x1 y divided by n, e 2p I x2 y divided by n, and the product of y over y, which is 1. So we finally we have this sum. Okay, now many of you probably expect and predict that this sum equals to 0, but some of you may not know why. And there are two ways to prove this. The first way is that this sum is the sum of all roots of unity of the power n and big. And this kind of sum always equals to 0. And the second way is to prove the first statement I just said by using this formula of the sum of geometrical progression. So let's apply the formula and see what happens to this sum. We have again this 1 divided by 2 in the power 0, and if we take y here as 2n, then this is going to self-destruct, and we will have in the numerator e in the power 2p I xy x2 minus x1 minus 1, and in denominator it would be just e 2p I again x2 minus x1 and 1 divided by n big minus 1. So this does not equal to 0, and this does because here we have some integer, and the exponent, complex exponent with integer number of these angles, 2p, always equals to 1. So we have 1 minus 1, and all the sum equals to 0. Thus, we see that QFT preserves not only norm, but angles too. Thus, it is unitary. Okay, everything is fine with QFT, and now we have to know how much would it cost us to implement it. First, we can see that this part here can be simplified, since the integer number of these two pi's in the power of exponent gives us 1, so we can keep only the fractional part of this fraction. Okay, now we are going to decompose this fractional part, xy modulo n divided by n. And to do this, we are going to need the bit representations of both these integers, x and y. So let's write x like x0 plus x1 multiplied by 2 plus x2 multiplied by 4 plus etc. and plus x n minus 1 multiplied by 2 in power n minus 1. Okay, and the same for y. Y equals y n minus 1 multiplied by 2 in n minus 1 power etc. plus y1 multiplied by 2 plus y0. So, if we multiply x and y, we actually multiply these bit representations, so these sums. And when we multiply two sums, we actually multiply each member, each term of the first sum with the term of each term of the second sum. But if we multiply, for example, this term by this term, we will get the power of 2 equals to n here. So it would be yn minus 1, x1, 2 in the power n. And when we divide by n, which is 2 in the power n, we get integer. So we don't get the fractional part, but we need the fractional part. So we remove all such elements from this product. And the thing that stays in this product is yn minus 1 multiplied by x0 divided by 2 plus yn minus 2 multiplied by x0 divided by 4 plus x1 divided by 2, etc. y0 x0 divided by 2 in the power n plus x1 divided by 2 in the power n minus 1, etc. up to xn minus 1 divided by 2. Okay, and now all this goes here in this power of exponent.